Hello everyone. In this lecture I shall discuss the second method to find the solution of algebraic and transcendental equation. In my previous lecture 2 I have discussed the regular falsi method. Right, regular falsi method I have discussed. Also this method is called the method of false position. Now this second method is an improvement over this previous method, regular falsi method. Where in regular falsi method we have the restriction of fa into fv is negative in every stages, right? But here in second method we do relax this condition, right? For initial approximation we have, but in subsequent stages we just relax this condition, and in this context this is an improvement of the second method. So here the graph of the function is approximated by a secant line or a chord. It is similar to your earlier regular falsi method, right? Since the graph of the curve is approximated by a secant line, this method is named as a secant method. Okay, as a result this method is named as a secant method, right? However, as I have mentioned, it is not necessary that the interval contain the root. Since in subsequent stage we are relaxing the condition fa into fv is negative, so it is not necessary that the subsequent interval contain the root, right? Accordingly we move. That means here the formula is same as the previous regular falsi method. Okay, so let me to write the formula. Of course the geometrical interpretation is same. Now before discussing the details of the formula, let me to introduce myself, Professor Kumar Paikray, currently working as a professor in the Department of Mathematics, Veer Surendra University of Technology, Burla, Odisha, India. So without much delay, let us now start with our second method, which is almost same as the regular falsi method, with just relaxing the condition of fa into fb negative in every subsequent stage. So let me write the formula. So in view of the necessary formula, we have to consider the initial condition as earlier, taking x0 is equal to a and x1 is equal to b as the initial approximations, that is here fa into fb negative. The necessary formula for subsequent approximation is given by xn plus 1 is xn minus xn minus 1 by fn minus 1 into fn. Here this f of n means f of xn. Okay, f of xn. Now this is the formula, and n varies from 1, 2, 3, so on. So this is the formula. Now here the most important thing is that we do not need, right? We do not need to check fa means fxn minus 1 into fxn negative, right? We do not need to check it, right? In every stage, in subsequent stage, right? So this is the difference here. In previous regular falsi method we always check it, but here we just relax this condition. Okay, we do not bother about this whether the root lie in this interval or doesn't lie, but we have the formula is same, but we ignore this. We no need to check this. Okay, so this is why this method is an improvement of this, right? That means here the convergence may not be ensured, but if at all it will converge, then it must converge faster than the previous method, right? If we simplify it, then here xn plus 1 will be given by xn minus 1 into fn minus xn into fn minus 1 divided by fn minus 1, okay, with relaxation of condition fn minus 1 into fn is negative, right, is negative for n greater than equal to 1, with this relaxation of this condition, right? Now this formula can be rewritten like this, and this condition is relaxed, but this condition is imposed in the previous regular falsi method. Now if I put my xn minus 1 is my a, and my xn is my b, right, then this formula will be same as xn plus 1 is afb minus bfa divided by fb minus fa. So this is my formula, okay. So as usual, we'll take a and b without looking into this restriction, right? So here, in view of the geometrical interpretation, is same as if our previous case. So in view of the geometrical interpretation, we consider the xy plane and we consider the curve y is equal to fx. Let this is my curve, y is equal to fx is my curve here, and this is my, suppose this point is my a point, and this is my f of a. So here this let this point be a, the coordinate is afa. So here fa is negative, is not it? And suppose this is my point b and this is my fb. This is my point b and this value is my fb. Now this point say is my b, here bfb, right? Now this curve is my y is equal to fx curve is given, okay. Now actually the x-axis cuts the curve at the point you say it is my alpha. So alpha is my root here, but for initial approximation, here we see here f of a is negative and f of b is positive, right? So root lies in ab. So root lies in ab. So now the final answer is alpha, but we consider the initial value in between a and b, right? And how we'll get a initial approximation here, right? We join a chord here, right? If we join a chord here from a to b, right, it intersects at the point say at x1, at x0 it intersects here, right? Now this x0 is a initial approximation here, okay. Accordingly if I draw a perpendicular here, right? Now let this point be my c point, this point be my c here, and now here what happens here, f of c into f of b is negative here. So now the root again lies in between c and b, okay. So we next join a chord here, okay. Now this intersects at x1 say. Now gradually we have the approximations x0, then we have x1, then gradually here x2 can be obtained by this formula, then here x3, and we go on considering xn, right? And you say this xn is approaches to our desired root. So this geometrical interpretation is same as we have discussed in our previous case of regular falsi method or method of false position, okay. So now let us discuss some remark in view of the convergence and discuss some important examples so that your idea will clear. In fact, coming to most important, as I have told, there is no guarantee that the sequence approximations generated by secant method will converge. Right? Convergence is not guaranteed. Right? Why it is not guaranteed? Because we relax this condition in subsequent stages. Right? But if at all it converges, then it is faster than your regular falsi method. Right? In fact, the rate of convergence of secant method is 1.62, whereas the rate of convergence of regular falsi method is only 1. Right? That's why it is faster. Right? So thus I can say convergence of secant method is not guaranteed because of this reason, because we relax this. However, if at all converge, it is faster than regular falsi method. In fact, this method is most economical, right, giving reasonably rapid convergence at low costs. For physical point of view, right, we use this method as a economical method. Now coming to the drawback of this method, right, the moment this denominator, this fn minus 1 is close to fn, then what will happen? If this is close, then the denominator becomes 0, right? At any iteration, if this fxn is same as fxn minus 1, then this method fails and shows the convergence doesn't necessarily converge, right? So this is a drawback or one of the pitfalls of secant method, right? Okay, now coming to the examples, let us discuss some examples. Also we compare this example with your previous regular falsi method so as to understand the rapid convergence of this method. So now you are asked one problem. Find the square root of 3 by using regular falsi method and by using secant method. Right? So one we are using regular falsi method. You see, let my f of x is what? X square minus 3 is equal to 0. Right? So for in view of the initial approximation, what is your f of 1? F of 1 is 1 minus 3 is minus 2 is negative, and your f of 2 is 4 minus 3 is equal to 1 is positive. Right? So as f1 into f2 is negative, so root lies in your interval 1 2. Right? Let my x0 is equal to 1, or this is my a, and my x1 is equal to b, right, is equal to my 2. So what is my necessary formula? The necessary formula for regular falsi method is xn plus 1 is xn minus 1 by fn minus 1 into fn, or if you simplify it, it will give you xn minus 1 fn minus xn fn minus 1 divided by fn minus 1, or we may write it a fb minus b fa by fb minus fa. Right? Where in each step we have to ensure that fn into fn minus 1 is negative for all for n greater than equal to your 1. Right? Also, so also here n is greater than equal to 1. Right? You may use it. Okay, or you may use it. So here now for fast approximation we have n is equal to 1, then here x2 is equal to here x1 x0 f1 minus x1 f0 by f1 minus f0. If you simplify it, here x0 is 1 into fb, here fb is 1 minus here x1 is 2 into f0 is your minus 2. Okay, f0 is your minus 2 into minus 2 divided by f1 is your 1, f1 is your 1, f1 is your 1 minus f0 is your minus 2, minus of minus 2. So this is equal to 1 plus 4 by 3 is your 5 by 3. 5 by 3. So this is equal to your 1.666667. Right, 1.666667. So now we have to find what is f of your f of x2, right, is f of 1.666667, and if you simplify it, it will give you minus 0.2221. It's negative. Anyway, it is here negative. You may check it. Okay, it is here negative. So since this is your negative, we have to search the immediate positive, right? At this it is negative, and the immediate positive value is this. So the root lies between 2 and this, right? So we write here as f of 1.666667 into f of 2 is negative. So root lies in 1.666667 comma 2. So for my second approximation, let here x1 and x2, right? Let this is will be my x1, this is my x2. So my x1 is 1.666667 and my x2 is my 2 here. And here what is fx1? As I have told you, it is 0.222222 6 number of 222 1, right? And here f of x2 is here 1 here. F of x2 is here 1 here. Okay, so now my what is my x3? X3 is equal to x1 f2 minus x2 f1 by f2 minus f1. If you solve it, you will get 1.72722727, right? And similarly you find f of x3, you will get it negative. It will be your minus 0.0165289. Okay, 289. It is negative. Since this is negative, we search for immediate positive. The immediate, this is my negative, this is my negative, this is negative, and my immediate positive is here. This is my immediate positive. So f of 2, clearly f of 1.727227 into f of 2 is negative. So root lies in 1.727227 comma 2. In this interval the root will lie. Now coming to the third approximation, we have here x2 and x3. Let my x2, this is my x2 and this is my x3. So my x2 is 1.727227 and my x3 is my 2 here. Accordingly my f2 is here minus 0.0165289. Accordingly my f3 is my 1. So my x4 is given by x2 f3 minus x3 f2 divided by f3 minus f2. If I simplify it, then it will give me 1.7317073. So if I go on continue, right, then my next Next my x5 will be 1.7320262 and my x6 will be 1.7320491 and my x7 will be 1.7320507 and x8 will be 1.7320508. You see here the accuracy up to 1 2 3 4 5 6, so it is correct up to 6 decimal places. It is correct up to 6 decimal places. So now we solve by the second method. You see how this second method is different from your regular falsi method. So your fx is this, accordingly your f1 is -2 negative, your f2 is 1 positive. So initially this we need. Okay, for initial approximation we need f1 into f2 negative, so root lies between this. So now the necessary formula is this, same as your second method, but here we are not going to subsequently check that fn minus 1 into fn is negative. This condition is relaxed subsequently. Okay, now this condition is here, but this condition is subsequently relaxed. Okay, now your first iteration, you see here for n is equal to 1, here x2 is here x0 f1 minus x1 f0 divided by f1 minus f0. So the necessary formula is this. So here this is your x0 is your 1 and here f0 is your -2, x1 is your 2 here, x1 is 2 here and f1 is your 1 here. Okay, so now if you simplify it, it will give you 1.66666667. Now unlike here, but you see here we get here f1 here, the same thing we are getting here, but we subsequently get what is fx2 and we check it, but this thing is being relaxed here. Okay, we just find fx2 is needed, but we don't need whether it is positive or negative here, right? Then my what is my x3 I find, then my x3 will be my for the second approximation, second iteration. So next year x3 is equal to x1 f2 minus x2 f1 by f2 minus f1. We need to find f2 here, but we won't bother about positive or negative. Okay, we need to find your fx2 here. If you find it will be minus 0.222221. We don't bother whether it is negative or positive. So as usual my x2 is my x2 and my x1 is my x1. Okay, as usual my x1 is my x1 and x2 is my x2. Okay, so this is my as usual x2 and this is my as usual x1. With this I proceed to work out it, and this will give me 1.727227. Then my third iteration I find similarly my x4. Okay, x4 will be 1.7321429, and similarly my fourth iteration is my x4 is equal to this is my x3, my fourth iteration. Your x4 will be 1.7320508. Okay, you see now at this fourth iteration we get this desired accuracy as we got in earlier case. We got it in 8th iteration, we get it. Okay, but in 4th iteration we get it. Clear? So this is what your second method. So we just need to find fx3 here, and we don't bother because in the formula we need to use it. Okay, we need to just a minute, this will be my this is x2, then in second iteration x3, and it is my x4, and this is my x5. Okay, this is my x5. Then we need to find fx4, but we don't bother positive or negative. Okay, so now this is my final answer. So therefore based on this both the methods, we conclude that the secant method is much faster than the regular falsi method, because at fourth iteration we are getting the result here, but in regular falsi method in seventh iteration we are getting the result. Now coming to one more example, you are given f of x is equal to here cos x minus x e to the power x. Okay, and we use the secant method to solve it up to correct up to 4 decimal places. Now coming to your solution, and here be sure that you bring the calculator to radian mode. Okay, radian mode, calculator radian mode, this is important. For while you find a trigonometric function, we bring the calculator to radian mode. Okay, so let my f of x is equal to cos x minus x e to the power x. So you find what is your f of 0. So this implies f of 0 is cos 0 minus 0 is your 1 here. Okay, and you find f of 1 here, it is cos 1 minus e, you find it minus 2.17798. This is your positive and this is your negative. Okay, as f0 into f1 is negative, so root lies between here 0 and 1. Okay, 0 and 1. So now we have the necessary formula, right? Necessary formula for secant method is given by xn plus 1 is equal to xn minus 1 by fn minus 1 into fn. Okay, or if you simplify it, it is xn minus 1 into fn minus xn fn minus 1 divided by fn minus 1 n greater than is equal to 1. So this is your necessary formula. So now coming to your first iteration. Okay, your first iteration for your n is equal to 1, your x2 is equal to x0 f1 minus x1 f0 by f1 minus f0. Now this is my f0, right? What is your x0 here? Your x0 is 0 here, x1 is here 1 here, and your f0 is 1 here, and your f1 is minus 2.17798. Okay, if you substitute all this thing, then your x2 will be 0.31467. Okay, we just find f of x2. It is cos x2 minus x2 e to the power x2. Substitute x2 here, then your f of x2 will be 0.51987. Okay, we don't need to check positive or negative. Okay, we don't need to apply the intermediate value theorem here. Then in second approximation, in second iteration or approximation, we have here n is equal to 2, implies your x3 is x1 f2 minus x2 f1 divided by f2 minus f1. Okay, so this is as usual, your x1 is itself is your x1. Okay, and f1 is itself f1, and your x2, this is your x2, and this is your fx2, means sequentially it will move, no need to rearrange it. Okay, so this if you substitute all these values here, right? If you substitute all these values here, then here x3 will be 0.44 0.44673. We just need to find what is here f of x3. It is cos x3 minus x3 to the power x3. If you substitute x3 this much, then here 0.20354. Okay, so then we have the third iteration. Here third iteration, what is here x4 will be x2 f3 minus x3 f2 minus f3 minus f2. So as usual this is my x3, this is my f3, and this is my x2, this is my x2, and this is my fx2. Okay, so you substitute all this thing here. We may spell it out here. What is x2, what is x3, and what is fx2, what is fx3, but we don't need it. Why will repeat? Okay, we don't need it. We just gradually substitute all these things. So after we simplify it, it is 0.53171. If you go on continue this process, right, in fourth iteration, here x5 will be, right, here x5 will be 0.51690. Then here fifth iteration, here x6 will be 0.51775. Okay, then here sixth iteration. In your sixth iteration, here x7 will be 0.51776. So you see here, so compare here x6 and x7. You see up to 4 decimal places, right, it coincides, right? So here the root is correct up to 4 decimal places. Okay, hence the desired root correct up to 4 decimal places is 0.5177. Okay, now coming to the summary of this discussion, the formula for regular falsi method is same as the formula for the secant method. However, in regular falsi method, the intermediate value property need to be checked in every subsequent stages. But here we relax that condition. Sequentially we will take x0, x1, x2, x3, x4, x5, so on. But in regular falsi method, we have to rearrange it. What is x0, x1? Then what is x1, x2? We have to rearrange it based on the intermediate value property. Okay. So this second method, the rate of convergence is 1.628. However, in regular falsi method, it is here 1. So second method converges faster. Okay. In some cases, second method do not also converge. Right. Why it will not converge? Because we relax the condition fa into fb is negative. If suppose fa is positive and fb is positive, they lie on the same side of the curve, then we don't find the root. Okay, this is the disadvantage as we have pointed out in the remark. So this is the disadvantage or drawback or pitfall of secant method. You can see it. Okay. So now with this, my appeal to all of you is that if you find that this lecture is helpful and interesting for you, then please subscribe to this channel. Also like this channel. You may also hit the bell icon so that whenever the new lecture will be uploaded, just you will get the notification, which will be easy to access. Okay, the video is getting lengthy, so we close it here. Thank you all.